Hi, I'm a computer science graduate student and was recently assigned a project to make a genetic algorithm to solve equations. I've been in university for less than 3 months now, so I thought, what? So in short, this video is going to be divided into 3 segments: a description of the assignment, a showcase of the code in action, and what I learned while working on it. So, imagine we have this equation. We start by generating random answers to it, which we call a population or generation, each answer being an individual. In this example, we have the individuals 10110010 and 01001111. Then we assess how good they are by doing the math and finding out how far they are from the result. The sorting is done based on this score. We could choose to stop for close enough, but obviously that's not the case here. Selective breeding is a crucial step to generate offspring that hopefully will be as good or even better than their parents. So for the first son, let's take the first half from individual 1 and the other half from individual 2. The other son's DNA will be created the same way, but alternating the parents. Mutation is another really important step that allows us to reach combinations that didn't show up in our first generation or that were eliminated after selection. Let's suppose the most significant bit of individual 2A gets flipped. If that's the case, this number is 194, our answer. The idea is to apply this to a quintic equation. Just as a side note, there's a GitHub link to the code in the description. You can check it out there and roast me for how poorly written it is. First, we start by choosing the coefficients a, b, c, d, e, and f. Then you can specify how close to the result it needs to get before stopping. I'll use -1 for the default value of 0.002. To avoid having a lot of junk being spewed out on my screen, I'll set the verbose option to n. Now we have 3 pieces of information here. Value is what we could substitute x for in the equation. In this case, the right side of the equation would be the opposite of the difference. Now the individual is an integer, as you can see, but it's nothing more than a representation of the value, which is a float. So how does it work? The process of converting the integer to a floating point number is done by this function. But you can only understand how it works if we know 1. How negative numbers are represented. A signed integer usually has 32 bits, and the most significant bit is actually used for the sign, 0 for positive numbers and 1 for negative numbers. But it's not as simple as calculating the number the rest of the bits represent, and only changing the first bit to have, let's say, 5 and -5. Computers use a thing called 2's complement. If we have 5 and want to find out what -5 is when stored in memory, we do 2 operations: invert its bits and add 1. 2. The exclusive OR operation. In no time, you'll be using a calculator to do the same binary operations that piece of code does. And to invert the bits of a number, we can use the exclusive OR operation. As the name states, if both are 1 or both are 0, we get 0. Now, only one of them is 1, the result is also 1. So let's see how we can invert the bits of 5 and base 2 by doing the short of each bit and 1. Okay, so now let's use a calculator to find out how that function turns this int into this float. If it seems a bit complicated, don't worry, that's the beauty of programming. We automate all of this so we never have to do it. Step 1, the number is negative, so we should apply the 2's complement rule to find out its bits. Remember, we need to invert the bits and then add 1. The short operation can be used to invert the bits. To get a number comprised of 32 consecutive ones, do the short and add 1. Step 2, the function splits those bits into 3 different numbers: the sign, which is the most significant bit, the exponent, which is the final 8 bits, and the mantissa, which is the rest. Step 3, math. Minus mantissa, because our sign is 1 divided by 2 to the power of the exponent, which is 28. Same way you can right shift decimal numbers by dividing by multiples of 10, we can do the same thing with binary numbers, dividing by multiples of 2. And bam! As I said before, I just got into university, and being able to apply what I already knew and what I learned here into a real-world problem was honestly quite fun. I try to focus on making the code as flexible as possible, so you can easily change it to work with more than one variable and stuff like that. Thinking and designing beforehand and then coding was something that helped a lot with this project, instead of just trying to spurt out lines as fast as possible. And last but not least, proper documentation, because we're not going to remember what we wrote yesterday.